Section 3.9 is dealing with what's referred to as differentials, and what you see here is, of course, the equation of just any line, but of course what this is in reference to is the equation of a tangent line. So this is your point slope form. Of course, this is just it rewritten with different notation. So they're using the letter C here just to represent some x value, because you always do x minus the x coordinate of the point. So they're using, like I said, C to represent that. Of course, slope, as we know, to find the slope of your tangent line, that is related to your derivative. So that's why you have your f prime at this particular x value. So that's going to be your slope. And of course, this is just your function notation. Like if C happens to be 5, then this is f of 5, which we know that that notation represents a y. Okay, now all right, so just some notation and terminology here that you need to be familiar with. X minus C is referred to as your change in X, which is going to also be noted as delta X. And when delta X is small, then the change in Y, which is referred to as delta Y. Again, this is just delta Y. That's those random dots there that are showing up. So this is just delta Y, and that's just a semicolon there. So the change in Y, which is referred to as delta Y, can be approximated by what you see below here. So to get your change in Y, then this is just doing your subtraction, okay? Now, this is what they actually refer to as your actual change in Y. If you want your approximate change in Y, then that's where your f prime of C times your delta X is going to come in for your approximation. Okay, it says for this approximation, delta X is typically denoted by dx and is called the differential of X. The expression f prime of X dx is denoted by dy and is called the differential of Y. So based on that, then you can make the statement or the equation that dy is equal to f prime of X dx. So that's what they're referring to as this differential form, okay? Now, all right, so this being the first one that we're going to look at. All right, so the function that we're dealing with is y equal x squared. And as it states, you're asked to find dy when x is equal to 1 and dx is equal to 100. Compare this value with delta y for x equal 1 and for delta x equal to 100. Okay, here's what you're going to do in a situation like this. And I'm going to show you a picture in just a minute of what actually all of this is. All right, you are going to need the derivative of your function. So let's go ahead and we'll say y prime is going to be equal to 2x, okay? Now, they're wanting you to compare your dy and your delta y, okay? So I gave you the equation just a few minutes ago. It doesn't matter which one we do first. I'm going to say dy. That's going to be equal to f prime of x dx. Okay, so using this, we've got our information that we can substitute in. So the x value that we're dealing with here is x equal 1. So that means I'll have f prime of 1. And we are told that dx is 0.01. Okay, I just went back and put this in a bracket. I don't want you to think that you're multiplying 1 times this, you're actually doing the derivative evaluated at 1 times this, okay? Now, your derivative is 2x, okay? So you need to evaluate your derivative at 1. So that means you need to take your 1, substitute it into your derivative, so that's 2 times 1, and then you're going to multiply this times the 0.01. And that's going to give us a value of 0.02. Okay. All right, now next, let's talk about the delta y. Okay, so I had written this down earlier in the notes. When we were looking at it earlier, they actually used the letter C, you remember, just to represent some x value. I just went ahead and put it in terms of x. All right, so we know that our x value, remember, is 1. And we were told that the delta x, remember, is the 0.01. And we're going to subtract from that f of 1. All right, so you can add your 1 and your 100th. Of course, that's going to give you 1.01 minus f of 1. Now, this time, of course, this is in reference to your original function. So you're going to evaluate your original function at 0.01 and then evaluate your function also at 1 and then subtract those values. So going back to your original function, which is y equal x squared, we need to first substitute in 1.01 squared minus, and then the original function evaluated at 1. And if you do these calculations, you will end up with this, okay? So you are asked to compare these two things. And as you can tell, obviously, they're very close to each other, okay? Now, if you remember, they referred to as, or in the notes, I referred to this as being the actual change in y, and this being your approximation, okay? Now, here's what the idea of what you're doing here, and this is just out of the textbook I was going to show you. All right, here is the graph. Okay, so this is your function here of x squared. Of course, this would come on down if you had the whole thing and come down and come through the origin, but they're just showing the part that starts with 1, 1, okay? So say our x value that we were looking at, see, is at x equal 1. Now, they had gone ahead and calculated and found that 2x minus 1, this is just the equation of the tangent line at that point, which you did not have to do that, you know, in order to answer the question. Now, remember the two values we found. We found dy to be 0.02 and delta y to be 0.021. And you can see here where they have those labeled. See your dy, so that means that you're dealing with here 200ths, and then your delta y is the 0.0201, okay? So the dy is using your tangent line to get the approximation, okay? Because, you know, we used our derivative, remember? If you go back, when we did dy, we used our derivative, okay? So that's what leans you toward the fact that you're dealing with your tangent line. So that's why this distance from here to here, see, comes over and they have it touching on your tangent line. And then your delta y, which is the actual change in y, see, comes back to the actual point. But it's just telling you that you can use this tangent line to get this approximation, you know, for the actual change in y. Because sometimes it's just a lot easier to work with your derivative versus your actual function, okay? So that's just an idea of what you were actually doing there on that problem. Okay, next. this would be an application of where you would see differentials used. This is area of propagation. Alright, so you're dealing with a ball bearing, and you know that its radius is 7/10 of an inch. If the measurement is correct to within 1/100th of an inch, estimate the propagated error in the volume. Meaning, if you allow your radius, like this is what it's to be, 7/10, but if you allow it to be off this much, then obviously if your radius is off a little bit, then your volume's going to be off a little bit. So that's what we're dealing with here. What is the error in the volume based on the error that you're allowed with your radius? Okay. All right, so we're dealing with volume. So we're going to want our volume formula for a sphere, because I mean a ball bearing is just the shape of a ball. So 4/3 pi r cubed. Okay. Now we're dealing with a radius of 7/10, but it can be off 1/100. So the change in your radius now, the reason why you would say that this change in radius is from negative 0.01 to positive 0.01 is you're just saying that you can go 1/100 less than this, or you can go 1/100 more than this. You're allowed to be off that much, okay? Now, you need your derivative. So I'm going to refer to this. Of course, you can do v prime or dv dr, because we are doing this with respect to r. So this is just your power rule. Your 4/3 pi is just a constant. Okay, so you're going to use your power rule, but if you end up doing the 3 times the 4/3, you're just going to end up with 4 pi, and then you reduce your power by 1. Okay, now to get your actual change of your volume, remember you can use the differential notation. Remember, this is an approximation of this, okay? So what we learned just a few minutes ago, to get this, you would do your derivative times dr, okay? That's exactly the same thing. Where did I lay that at? So that's exactly the same thing that we were doing just right here, okay? It's just I'm putting it in terms of V and R, okay? So this is dealing with your volume. And of course, instead of having an X value, then we're dealing with radius. So if this is your derivative, f prime of x dx, and now we have f prime of r dr. Okay, so it's exactly the same thing. I'm just adjusting the variables, okay? All right, so we need to evaluate the derivative at .7. And then our dr can be plus or minus 0.01. Okay. So we need to substitute this into our derivative. So remember, our derivative is over here. So we'll have 4 pi, and that would be 0.7 squared, times plus or minus 0.01. Okay. Now, you can just enter this in your calculator as all positive, but of course you're going to end up with it being positive or negative, but you can just enter it in all positive to do the calculations. So you're going to get plus or minus 0.06158, and that would be inches cubed since we're talking about volume. Okay, so this just means if you allow this radius to be off 1/100, 1/100 less, 1/100 more, then this is how much the volume's going to be off. It'll either be this much over, or it'll be this much under of what that volume would be, like we didn't have to calculate it, but like if you calculated your volume for exactly, 7/10, then this is how much it would be off. It would be this much over or this much under.